this is like a fraction of a second to exploit these kind of things. Right, so interesting suspects if you want to look into reference counting issues. Most kernels have interesting structures or objects that use reference counting. Things that come to mind instantly are VM areas and files, and there's probably a whole bunch of other things. The X server does some reference counting of some structures. There's Mozilla XPCOM, which is apparently a really ugly clone of Windows COM. Because, you know, the Mozilla guys thought, you know, this is a really nice way to do programming. Let's have XPCOM, right? Obviously, there's DCOM and COM Plus from Microsoft, which I've been told have some, or used to have some reference counting issues. JavaScript. JavaScript apparently does a lot of reference counting of a whole bunch of objects behind your back. I don't know this for sure because, you know, I try not to look at browser code, but I've been told by some browser developers that this is the case. And then apparently Python relies on reference counting for all sorts of things. I don't know this either because I don't like to look at Python internals because my eyes start bleeding. And there's a whole lot more of things, potential, you know, huge programs where you might get reference counting issues. Right, the next one is, so special case of file race conditions. And this one's, I find it rather interesting. So you sort of have this case in Unix where you have an SUID where you want to sort of try and safely reopen a file in a publicly writable, world writable directory. And so people have known for ages that it's difficult to do these things, but at some point somebody stood up and said, this is how you do it in a safe manner. And so what they've come up with is what I call the LSTAT open fstat dance, where basically you get a file name of a file that you want to safely reopen in a publicly writable directory. And before you open it, you call LSTAT on it. And you call LSTAT because LSTAT doesn't follow symlinks, and that means you can instantly see if it's some kind of symlink, then it's probably bad and, you know, bail out. Right? And then you still keep the stat structure in memory. You call open, and before you do anything to this file, you call fstat on the file descriptor. And then basically you compare the stat structure of fstat with lstat. And people, you go like, what people basically do is, if they compare the stat structure and they see if it's this exact same inode number and it's on the same device, then it must be the same file and we don't have a race condition. Unfortunately, this isn't true. There's still a race condition, and this is because between the lstat and the fstat, you might still be able to delete this file and create a symlink to something else, which just happens to be on the same device and has the same inode number. Because you removed this file which had this inode number and device, and then you might be able to create another file which is on the same device and gets the exact same inode number, because the inode number just got freed because you deleted something, right? And so apparently people haven't really picked up on this yet. So this means that there's still a race condition and that using this lstat open fstat thing is still insecure and you should never do this. So, you know, I've talked to this about some people and they go like, no, this isn't true. If you compare more structures from the stat structure, then it's totally safe. You know, don't worry. We've seen all these things. It's completely safe. But it's not. And so here's the entire stat structure. And I'll walk over them one by one and see exactly what they do, and then you can sort of see, well, you can spoof all of these things. Well, sort of, you know, or fake them, right? So the first one is it has to be on the same device. Well, okay. That's usually not really a huge constraint. It could be, but it usually isn't. It has to be the same inode number. It's a bit annoying, but depending on the file system, it's usually realistic to delete a file and then create an arbitrary other file with the same inode number on the same device. It takes some work, but it's realistic to do this. Has to be the same mode. Okay, it's a constraint, but it doesn't prevent the race condition. It has to have the same amount of hard links. Well, who cares, right? Has to be owned by the same user and group. This might eliminate some cases, but it doesn't stop the race condition, right? It's still there, and I'm sure there's a bunch of cases where it's okay to where they compare the UID and GID, and where it's okay if they match. The next one is basically where the file has to be the same size. I guess this might be a problem in some cases, but it doesn't prevent the race condition. And then the block size doesn't really matter because it's usually the same for all files across one file system. The block count is sort of like the file size, but it differs if you have sparse files. So again, this does not prevent the race condition. And then so basically you get the file timestamps. And so people kept telling me, compare the file timestamps because that's what makes it secure. That prevents the race condition. So I started thinking about this and like, well, these are time t's, and time t is the time measured since epoch. And epoch is January 1st, 1970, right? They're measured in seconds. Computers are really, really fast these days, and I bet I can win a local file race condition within a second. So even if you compare these things, they don't really add that much, right? And if you fail within that second, there's not really a problem because you can just try again and again and again until your race works within that one particular second. So you get a whole second to race. Depending on the way you mount your file system, A time doesn't really matter because it doesn't get changed. And then if none of these things help, you can just wait for 70 years. Time t's overflow, right? I think 2038 or 36 is when it starts overflowing, right? So if you have enough time on your hands, just wait for a while. So if you're an attacker, you're in luck because if people would compare all of these fields, it wouldn't prevent the race condition, but it would make it really, really, really difficult for you as an attacker. People usually don't compare like all of the fields because who would want to do that, right? They usually just compare the inode number and the device. Sometimes they look at the number of hard links. Sometimes they look at the mode. I haven't really seen anything else besides that. So if you're an attacker, you're in luck. If you're trying to write code that safely reopens a file in a publicly writable directory, I have bad news for you. You can't do it. It's impossible to do it safely, as far as I know. So somebody else came up to me and said, well, you can prevent this race condition by, if you call open, say, oh no follow. And what oh no follow means is that it won't follow a symlink. Unfortunately, this particular person was wrong because you don't necessarily have to have a symlink, right? Because the case basically that the whole case of this thing is if it has the same sort of attributes, it must be the same file. But it's not true. It could be a totally different file, right? The symlink is basically just a way of easily exploiting these things, right? So using onofollow, first of all, doesn't prevent the race condition. There's still a race condition. Second of all, onofollow is really not what a lot of people think it does, right? It actually does follow symlinks. It just doesn't follow symlinks at the end of your path. It follows directory symlinks. It does not follow file symlinks. So there's still cases where even onofollow won't save you if you use a symlink. But in a general case, onofollow prevents an attacker from using a symlink, but that's it, right? So let's say you might be able to use a hard link if people forget to check for the number of hard links in their check. And even if they don't, you might be able to force an application to create the file with the exact same name and the exact same inode number and the exact same device, but with a totally different content. So yeah, file race conditions. So basically, safely reopening a file in a world wide directory is impossible. Don't try it. There's piles and piles of vulnerable applications that do try it. Audit them. You'll find lots of cool bugs. Trust me. So moving on to regular expressions. Regular expressions are often used for input validation. And if they're not used for input validation, they might still be used for some kind of pattern matching in security-sensitive context. Snort, for example, right? The thing with regular expressions is that they're this odd-looking things, and nobody really knows all the details of how these things correctly interact with each other. So it's really hard to get regular expressions exactly right, right? They might look like they pass whatever you give it to, but there might be some corner cases that you're not aware of. Even really simple regular expressions are not always what they seem. So I ran into this thing in a web application where they wanted to get some number as input, and that was it. They didn't want anything else. Because this would have gotten written to a line-based configuration file, and if you gave in something else, it might be horribly wrong. So they used this thing where they end with a $sign, and they start off with this sort of hat thingy. And I have no idea what the caret is called, so I'm just going to call it the hat thingy. Do you know what it's called? The caret? Okay, so it's the caret. Thank you. And so it's sort of the caret and then a few numbers, dash, a few more numbers, and a $sign. That's it. And so what this means is basically I want to have a line which is just that and nothing else. If there's anything else in there, I'm going to fail it. It won't match. And that usually works, the problem being that the $sign also matches the next line. As it turns out, in this particular web application where I found this thing got written to a line-based configuration file. So you get next line injection, and that was kind of catastrophic. Well, hey, I did some Googling for regular expressions, and I have no idea what this thing does, but it looks horrible. So if it's difficult to get this right, nobody can get this right. Right? And somebody else also wanted to make a huge regular expression, and he couldn't get his regular expression compiled by GNU regex because GNU regex has actual limitations on the regular expression used. The string can only be 65,000 characters long, and you can only have 255 pairs of brackets, and a few other things, right? If you're hitting these kind of limits with a regular expression, then it's not the problem of the regular expression engine, it's your problem, right? Regular expressions should really not be this long. It's insane, right? Apparently people do want to make long regular expressions. I have no idea why. So these are just some usage issues with, these were usage issues with regular expressions. Now it more comes down to the implementation, right? Some regular expression implementations are not binary safe when they're matching stuff. What that means is for example, the PHP erect function is not binary safe. And what that means is you take a piece of input, untrusted inputs from a web application, and you use it in your erect to match against something. But it's totally untrusted. What this means is there could be 0 bytes and whatever in there. And PHP erect, the erect function, basically doesn't really do anything besides pass on all the data it gets to a C API. And C has this notion of how strings have to work. And strings end the moment you see the first 0 bytes, right? They don't really care what's after it, right? The first 0 byte you get is where the string ends. So you give in this huge string into PHP, but for example, you give the first part of it is something that matches the regular expression, and then right after it you add a 0 byte, and then you add whatever stuff you want that might not match, right? And so erect passes this on to, passes on to the C API, and the C API goes like, oh, this thing matches, and it goes back to PHP, and then PHP says, oh, let's put this kind of this string we got from the user, which now matches, A to Z or something like that. Let's put this in a SQL statement and pass it on to Oracle or whatever, right? And that's obviously problematic because the PHP erect function didn't really match everything, and there might be SQL injection or something similar like that in there. And turns out these kind of things have actually happened, and there's this sort of pen testing group in Germany called Red Team Pen Testing, and they found some of these issues, and I found this to be really cool. More issues with regular expressions. Some people apparently think it's reasonable to take an untrusted regular expression as input. I think this is bad because regular expressions were never built to handle untrusted input, right? They handle constant data, static data that people put some thought into it and where they know it's correct and where it's probably not too long because otherwise nobody can understand your regex. And so it was only built to be used in a way where the input would be trusted. And so taking regex input is usually